The Spa at Bath is one of the best-known monuments of Roman Britain, probably founded within our period. Indeed, the words Roman Britain conjure up, in most people's minds, stone buildings, roads, and Hadrian's Wall. But in the early years of the Roman occupation, the army built not in stone, which takes time and is not always available, but in turf and timber, readily to hand in southern England. The problem for us is that wooden buildings do not survive above ground. This field, for example, is the site of a large wooden fort known as the Lunt, near present-day Coventry, dating from about AD 60. But the archaeological evidence for it is little more than post holes and trenches. None of the wood survives, and indeed it's sometimes argued that the army dismantled their buildings and took them with them as they became needed elsewhere. So, without the buildings themselves, how can we begin to visualize what such a fort would have looked like? This painting by Alan Sorrell shows an outer perimeter of ramparts with gateways, and inside a complex of buildings which included barracks, a strange circular enclosure, and granaries on stilts. But in order to learn how such a fort would have functioned in practice, you need more than an artist's impression. Here at the Lunt, some of the buildings have been reconstructed, though since the exact details of the buildings are not known, the word simulation is preferred to reconstruction. The discovery of this curve in the ditch gave the first clue to the existence of a unique circular structure, over 100 feet in diameter. It's thought to have been a ring for training horses. The depth and dimensions of post holes give some indication of the height and weight of the building above. The posts supporting this gateway were massive enough to suggest a two-storey structure. The superstructure is based on a standard Roman design, which is illustrated on Trajan's column. The walkway is supported by turf ramparts, again a standard construction method. The most recent building to have been simulated is one of the three large granaries. No wooden Roman granaries survive, but at Corbridge in Northumberland there are the bases of stone ones which show how the building was raised off the ground to keep out damp and vermin. At the Lunt, the only evidence for the granary was a network of over 100 post holes in trenches, but this pattern is enough to imply a raised building. As with the gateway, the timbers for the granary were prefabricated in the workshops of the Royal Engineers. A fortnight was allowed for the actual construction on site. This was thought to be the maximum the Roman army would have been allowed for the job, being often under pressure in hostile territory. The completed granary is now used as a museum. The details of the building are to some extent conjectural, the slope of the roof, for example. But the most far-reaching implications are raised by the very existence of three granaries like this on one site, holding a total of over 500 tons of grain. When it was on campaign, the army foraged, but once established in permanent stations, it would have needed regular supplies of British grain. How were the British able to support a Roman army of 50,000 odd, not to mention the bureaucracy in the new towns, on top of their own population? How sophisticated and intensive was their agriculture? For the past 10 years, questions like these have been investigated at Butser Ancient Farm Project in Hampshire, using a more complex and radical kind of simulation. Using what evidence there is from archaeological remains and classical writings, they apply Iron Age methods and examine how grain and other crops actually behave in practice. One important area of research is grain storage, and in particular the large pits which are found all over Iron Age sites in southern Britain. Dr. Peter Reynolds, director of the project, explains.
The reason for our interest is that these have often been described as storage pits, storage of grain specifically, although other commodities could well have been put inside them. Fundamental questions are raised if this is precisely their function, simply because of their basic capacity. Each pit, for example, of that size will contain over 2 tons of cereal product. A considerable product if you think of the supposedly subsistence agricultural system that was obtaining at that time, if the academics are in any way correct.
To test one of these storage pits, Peter Reynolds fills it with grain, seals it with clay and rubble, and leaves it over the winter. He inserts instruments to measure temperature and humidity and to sample the atmosphere. This has demonstrated that the most important factor in this method of storage is carbon dioxide. Once the pit is filled and sealed, the grain uses up all the available oxygen in its normal respiration process and produces carbon dioxide as a waste product. This prevents the grain germinating and kills off harmful microorganisms. So the grain is preserved in a state of dormancy.
Now we've filled the pit and established that it's the same level as the floor, we're going to cap it with clay, standard process to provide an impermeable seal to the whole exercise. Afterwards, a rubble capping on top of the impermeable seal will keep it fairly sound during the winter period. One of the most interesting results that we've achieved from the storage of grain in these underground pits has been the discovery that you can store grain in such a way that the germinability is unimpaired. Now this is quite critical because it actually means you can store seed grain in a hole underground. This changes the whole concept of how we understand domestic and non-domestic storage systems in the Iron Age period. For example, no longer can we think of the pit as a resource in a domestic condition. We have to think of it rather as a warehousing facility. And as such, this begins to explain comments by Strabo, who describes one of the major exports from this country to the continent as corn.
Peter Reynolds believes that this implies an advanced agricultural economy in Iron Age Britain. And he goes so far as to suggest that the British grain supply was the main reason for the Roman invasion. This idea needs careful scrutiny, but it's based on a great deal more than just storage pits. His project covers a wide range of agricultural activities, at the farm itself, and at this more accessible demonstration site at the bottom of the hill. Here they keep farm animals. The cows are Dexters and Highland cattle, the nearest in bone structure to the extinct Celtic shorthorn of Iron Age times. These are Soay sheep, an ancient breed which survives on the Scottish island of St Kilda. The wool can be plucked and doesn't have to be sheared. In the middle of the demonstration site is a reconstructed Iron Age house. This is based on the traces of a house at Pimperne in Dorset, and the circular plan is characteristic of the British Iron Age. It has 4 tons of thatch on the roof, but despite this weight, the roof structure is quite strong enough without any central support. It has a floor area of 150 square metres, a very large house by any standards. It has been standing now for 6 years without any need for major repairs. But for the understanding of British agriculture at the time of the Roman invasion, the most important study at Butser is grain. As well as storage, Peter Reynolds covers the whole cycle of grain production, from soil preparation to harvesting. We're going to follow through the cycle of wheat production and see the sort of problems which arise, and some of the questions which have to be posed, in order to find out about British grain production at this period. The cycle begins in autumn, with the preparation of the soil. Yoked by the horns, these Dexter cattle pull a plough of Iron Age design, called an ard.
Well, now, what we've got here is a very simple ard, so-called, because it doesn't have a mould board inverting the soil like a modern plough. Primarily, we can compare this one to the Roman ploughs, where we have a main beam, and on either side, flanges of wood coming out at an angle, which spread the soil away from the furrow. It mimics exactly all the prehistoric ploughs. It accords almost word for word with Virgil's description of the crooked beam, the crooked handle, and then, of course, the bini aures, or two ears, projecting from the side of it. In real terms, all the prehistoric ploughs are extremely efficient. In terms of cultivating the soil, they actually stir the soil up, and they cultivate only the top 15 centimetres of soil, because this is the fertile area. Perhaps one could argue the worst thing that happened to agriculture was the turnover plough drawing up the subsoil into the upper layers. When you use this kind of plough, you cultivate the growing zone in the soil structure.
From archaeological evidence, we know that there were two principal varieties of wheat grown at this period: spelt wheat and emmer wheat, both very different from modern hybrids. These varieties survive today, but for evidence that they were grown as crops 2,000 years ago, we have to rely on pollen grains, seed impressions in pottery, and, most important, carbonized seed.
This is carbonized seed of emmer wheat and comes from an Iron Age site, and it allows us to identify this and other cereals that were grown at the time. One doesn't willingly turn the yield of a crop into carbonized material for archaeologists to find 2,500 years later. So we've got to really consider the finds of this stuff, first of all, as pure luck on our part, allowing us to understand the farming process, but secondly, that this is the product of an accident. It's unlikely to be a deliberate program of activity to turn this into carbon. Consequently, we really have to think of these finds as being the products of fires, bonfires, more predictably than any other system, because that's where we're going to get the anaerobic atmosphere, which will change this kind of starch material into carbon.
Many other plant seeds are found in carbonized deposits, including crops, like these Celtic beans. Others are more likely to be weeds, but the weeds are important because they were competing with the crops.
Carbonized seed is always a mixture of grains and arable weeds, and consequently, in order to get accurate yield figures, we need to grow specialist arable weeds which are now virtually extinct. Here we're standing in the middle of a crop of corn cockle. This is a living population of a plant which is now virtually extinct in the United Kingdom, but once, in the Iron Age, was a dominant arable weed. The seeds of this particular variety, one can readily see how easily they would carbonize. If we break the seed pod open and tip these into the palm of my hand,
we can see very hard, black, roundish seeds, very distinctive, very easy to recognize, and these come out as a dominant arable weed species in the carbonized seed programs.
One interesting side effect of our analysis of carbonized seed from excavations of Iron Age sites has been the isolation of this particular plant here, called Canopodium album, or fat hen. We've analyzed it successfully to suggest it might have been a catch crop in the prehistoric period. The seeds can be ground down and made into flour, and therefore into bread. The leaves can be eaten as a fresh vegetable, and the whole plant can be dried and fed to animals as fodder during the winter period. As such, it fills in a tremendous gap in our understanding of the prehistoric potential crops that we have from this basic evidence of carbonized seed.
So wheat and other Iron Age crops are grown together with an appropriate selection of weeds. The important question is the yield of the crops under these conditions. But first, there remains the problem of how they were harvested.
Here inside the research crop, we're admirably placed to compare and contrast prehistoric and modern varieties. Here we've got one of the best of the modern varieties called sicko wheat, and if we examine its general stand height, we can see that a range of about 20-25 centimeters actually covers the full variation between the lowest and the highest fruiting bodies. When we compare it with Emma wheat, we get a tremendous variation. Here we're looking at the lowest or a lower member of the fruiting bodies within the crop, and if we compare it here with the tallest, we're looking at the range of about a meter, standing from 60 centimeters way up to 120, 130 centimeters high. This causes enormous problems when we try to understand reaping systems in prehistoric and Roman periods. The classical references, for example, tell us that they reaped only the ear of the prehistoric cereal. In other words, we presume that they just cut off or picked, we're not even sure of this fruiting body here, the spike. Here we've got a replica of an Iron Age sickle. They're commonly found on Iron Age sites, or at least a large number have been found on Iron Age sites, and ordinarily we find them interpreted as sickles for harvesting. Now, as we said earlier, when we look at an object, what we're interested in is its function. And in this case, we need to test that function against the growing crop. And we've found in our research that it's impossible to use it efficiently. For example, if we take a bunch of ears and we draw our hand up to get a reasonable cut, we find that of all the disparate stand heights within this natural plant, we've reaped two, one with a long piece of straw and one at the ideal position. And it would seem that the tool itself is most inefficiently designed for this purpose. Consequently, we need to go back and examine the plant again. And we find that this brittle neck between the ear and the stalk is such that it's very simple to break it off. In other words, to pick the crop. In terms of harvesting, of course, the Romans brought their own innovations, which changed, and indeed a change which lasted throughout the centuries. This is a replica of a Roman scythe, and with it, it brought its own problems, because simply using it to take the base of the crop, what we do is create a mixture of straw, weeds, with all those seeds being brought into the farmstead, and of course creating enormous problems in purity of harvest. At the same time, however, over in Gaul on the large plains, they'd created a new machine, a machine which was an innovation not taken up again for nearly 1,800 years. And this, of course, was the vallus, the Celtic reaping machine. The evidence for this machine comes from two of the classical authors, Pliny and Palladius, who describe on the plains of Gaul a machine devised by the Celts for reaping their harvests. Effectively, we have a sculpture at Virton in Belgium which gives us this particular picture. Wooden wheels, of course the Celts invented the spoke wheel anyway, and this particular device, which represents the basis of the modern reaping machine anyway, but nonetheless, the purpose of the teeth is to drive into the crop and just to nip off the tops of the cereals. In other words, what the Celts are doing, are continuing what was the prehistoric practice of reaping the ears of wheat. Whatever the mechanics of emmer wheat and spelt wheat as crops, stand heights and all the other factors we've discussed, the basic question that we've been asking is what kind of yield factor you're going to get. And as far as we're concerned, with the results over some 9 years now, we've achieved a regular product of 1.5 tons to 2 tons to the acre. This poses enormous problems. First of all, it's quite capable of sustaining a very large population, so much so that we begin to think in terms of labor-intensive industries with a population perhaps approaching 4 million at the end of the Iron Age period prior to the Roman invasion. Given that, we have enough produce to feed 4 million people and still export. With that kind of yield factor, it makes sense. We can compare it directly with the average yield that was produced in this country in 1910 of 1,100 weights to the acre. So perhaps we're looking at Iron Age technology, which produced a yield factor in excess of anything that was then achieved until 1947-48 AD. So we have a technology which is more persuasive for Roman invasion than any other idea. The gold in Wales is very attractive, but it's not high in quality or in quantity. The real Celtic gold, the real reason the Romans invaded this country, in my view, is emmer wheat and spelt wheat. This is the real Celtic gold. The reason why England can properly be regarded as the breadbasket of Europe in the prehistoric period.